All right, here we go. We've got a question about calipers, mass balances, etc. Okay, hopefully you've tried this question, and yeah, let's get to it. So first thing to note here, we've got the caliper and we've got an example of a zero error. What does that mean? Well, when we close the calipers, we notice that we don't read 0, we read minus 0.3 millimeters. Obviously, when the calipers are closed, there's 0 distance between them, so this shouldn't be the case. And that is going to be important to later. You always should pay attention to these things to make sure that we're we're covering everything that they've got in the question. Now, your first thing that you're asked is to calculate D. All right. Now, the D, I won't put the thing back on the screen here. We had 20.6 and we have a 0 error of minus 0.3. And so therefore our D is actually 26.9 millimeters. What this means is that everything's being under measured. We need to add 0.3 millimeters to every single value in order to get the correct value. And the way that I've written this here is that D is equal to X minus Y, and that's important for later. In fact, it's important for right now, because a lot of students make a mistake here. We're asked to calculate the percentage uncertainty in D. Now, generally, we tend to think of uncertainties as being, well, I've measured the distance, and therefore that distance has an uncertainty equal to the smallest division. Well, actually, that's not true here. Delta D is equal to delta X plus delta Y. In other words, because we're subtracting these values, I add together their uncertainties. Now, each of those values has an uncertainty of 0.1. So actually, the uncertainty in D is the uncertainty in X plus the uncertainty in Y. 0.1 plus 0.1 is equal to 0.2. Now, I have seen many students not consider that, okay? A lot of students will miss this, okay? They'll get their first mark, but they'll probably not get this mark because they don't realize that that's what we're doing here. And it's a very subtle point, but it's one which is important for now. Don't worry if you missed it the first time. So in this case, you would get a much smaller percentage uncertainty. And I noticed even in the answers, this is written as 1%. I would put this as 0.74%. More about that in a second. You can have error carried forward here, of course. It means that if you make that mistake once, you will be able to recover from that later. Okay. A word on this 0.74, the reason I put the arrow here. On the mark scheme, they put it as 1%. Now, I think 1% is quite an ambitious number here. Okay, I wouldn't put it down as 1%. I'd leave it as 0.74. You are not going to lose marks for that, okay? There is no rule on percentage uncertainties like there is on absolute uncertainties to state things to one significant figure. Absolute must be stated to one significant figure, percentages don't, okay? Now, if we go on to B, we're asked one way in which the procedure could be improved. Well, let's just think about that, 0 the caliper. I was quite amazed. I wrote that down as a bit of a joke, and then I saw that that was actually an answer. Okay, I mean, I would suggest more things. Measure in multiple occasions is a really good one. There was a previous question about a wire with varying thickness. Well, the ball might have varying diameter as well. Okay, so measure multiplications and 0 the caliper. That's more than enough for that one. Next one is our good old friend, the percentage uncertainties again. Okay, we're being asked to calculate the density of the sphere, and we're told the value of the density of the sphere, and they told you how you calculate it, and that's going to be important later. It's really interesting. This is an occasion where you are given an occasion, where you don't have to use it. What you have to do is use it to make the uncertainty analysis. So let's do that. We're going to do delta rho over rho is equal to delta m over delta d cubed over d cubed. And why is that? Well, because we've got this equation. This is multiplication and division. We know 6 and pi have no uncertainty, so really we're looking at the percentage uncertainty in m and in d cubed. We're given delta m and m in this part. We'll use them in a second. However, we are not given delta d cubed over d cubed. What we are given is delta d over d. You calculated that here. So you are expected to use your percentage uncertainty here to get your values here. All right. Now, the bit that people struggle with here is again this idea that delta d cubed over d cubed is 3 times delta d over d. Okay, we don't know delta d cubed over d cubed. We know delta d over d. To get them, all we do is multiply by that factor 3. We're going to plug in our numbers, and we're going to end up with our percentage uncertainty. And I got here 2.6%. Again, this is different to the mark scheme, but there's no reason that you won't be penalised by that. Okay, to give loads and loads and loads of multiple significant figures here is not required. Okay, the last thing we're going to do is we're going to find the value of rho, all right, which is going to give you delta rho equal our percentage uncertainty times the value. The value is given in the equation, no need to calculate it. We've got 2.6% there. we're going to get 0.29, which gives you a 0.3. Remember, we present our uncertainties to one significant figure, okay? And then I'm going to present it this way, 11.3 plus minus 0.3. Now, interestingly, in the question, because they rounded up the percentage uncertainties, yeah, then they actually get a higher, in the mark scheme, they get a higher uncertainty, and it's closer to 0.4. So actually, you'll notice in the mark scheme it says 0.4. I'm still going to get the marks here, because this would be carried almost like an error carried forward, all right? As long as I've used my numbers correctly, it's fine. Okay, so giving an extra bit of detail here meant that my percentage uncertainty is a bit lower, meant that this value is a bit lower, it meant that this value became a 0.3, not a 0.4. Absolutely fine, don't stress about those things. As long as your process is correct, you're absolutely fine.